Hi everyone. In this lecture, I'm going to explain functions, their mathematical definitions, some of their properties, and then finally I will explain uh, Boolean functions, which are a specific type of function in math that we use a lot in computer science. So we start with some preliminary definitions of functions. First, we define the function itself. We say a function f that maps elements of set x to the elements of set y is a subset of the Cartesian product of x and y, which means that f should be a subset of x and y. That's the first condition. The second condition says this: for every element x in the first set, which is x, there is exactly one y in y such that x and y is an element of f. So what does it mean? We have two parts in the second condition. This is the second condition, this was the first condition. In the second condition, we have two parts. There's an one and only one part. When we say there is one y, it means that there should be at least one element in the second set y. When we say only one, it means that there should not be more than one element y in set y. What does it mean? Let me represent it using formal quantifiers and formal quantifier statements. The second condition has two parts. This is the first part in closed brackets, and this is the second part in the second closed brackets, and as you see, there's a conjunction between them. So what does the first part say? The first part says for every x in x, there should be a y in y such that x and y is an element of f, which means that for every element in the first set, which we call it domain, there should be an element in the second set, which we call it target, such that x is related to y by f, which means x and y is in set f. That means there should be at least one element in the target for every element in the domain. Now, let's look at the only one part. This is the one part. This is the only one part of this condition. What does the only one part say? It says for every ordered pair xy and x1 and y1, and for any other ordered pair like x2 and y2, if the first entries of these two ordered pairs are equal, then the second entries of the ordered pairs must be equal. This is the same statement that we said before, which means for every element in the domain, there should be at most one element in the target, which means that if the first entries x1 and x2 are equal, the second entries has to be equal too, because if the second entries are not equal, it means that one element in the domain is mapped to more than one element in the target. So after defining functions, let's talk about a little bit, let's talk about some notations regarding f. So this is the way that we represent a function from x to y. We write f column x as the first set, which we call the domain. This is a symbol for maps to, which means x maps to y, which is the second set in the function that we call the target. So this is a notation to express the fact that f is a function from x to y. Now, the set x is called the domain of f. The set y is called the target of f. Sometimes they call it codomain too. The last fact is that when we say f maps x to y, which means x and y is in f, or we say x is related to y by f, this can be represented by this equation. F of x is equal to y. That means x is related to y by f, or f maps x to y, or x and y is in f. So these notation, they all mean the same thing. There's an interesting representation of a function with a small domain and target, which we call it arrow diagram. In an arrow diagram for a function like f, the elements of domain x are listed on the left hand side, and the elements of target y are listed on the right. So if there's an arrow from one of the elements in the domain like x to one of the elements in the target like y, then we say x and y should be in f, which means that the ordered pair x comma y is in f. So if we have a ordered pair like this, we have to draw an arrow from x to y, and if we draw an arrow from x to y, it means that the ordered pair x and y is in f. So let's assume that the domain x is w, x, y, and z, and the target is a, which is a, b, c, and d. So a function f which contains these four ordered pairs w and a, x and a, y and d, z and c can be represented using this arrow diagram. W, x, y, and z, which are the elements of domain, are listed in the left hand side. A, b, c, and d, which are the elements of target, are listed in the right hand side. And w is mapped to a because there's a ordered pair like w and a. Also, we have an arrow from x to a, which means x and a is in f. We have two more arrows, one from y to d, the other from z to c, because we have two ordered pairs y and d and z and c in function f. The next definition in functions is this definition of range. Range of a function is different from, is not always equal to its target, but it is always a subset of the target. Range of a function f from x to y is defined in the following way. All the elements in the target such that there is an x in the domain in a way that x is mapped to y. So every element in the target that has an element from domain mapping to it is an element of range. So in this example, a, which is an element of target, is also an element of range because, for example, w is mapped to it. B is an element of target, but it's not an element of range because because none of the elements in the domain are mapping to B. C and D are also elements of target, and they are also elements of range because for C there's an element in the domain like Z that is mapped to it, and for D there is an element of domain like Y that is mapped to D. So the range of this function is A, C, and D. Obviously, A, C, and D is a subset of A, B, C, and D. So range is always a subset of target. Another terminology that you need to know is when we say two functions are equal. Two functions like f and g are equal if and only if f and g have the same domain and target. That's the first condition. And f of x is equal to g of x for every element x in the domain. So the functions f and g are equal if and only if two conditions are true. What's the first condition? They both should have the same domain and same target. What's the second condition? For every element like x in their mutual domain, f of x should be equal to g of x, which means that both f and g should map x to the same element in their mutual target. Next, we define the three properties of a function. Let's assume that you have a function with target y and domain x. So f maps x to y. We say this function is injective or one-to-one if and only if for every element x1 in x and x2 in x, for every two elements x1 and x2 in the domain, if they are both mapped to the same element in the target, which means that if f of x1 is equal to f of x2, then x1 and x2 must be equal. So what does one-to-one property mean? It means that if two elements in the domain are mapped into the same element in the target, then those two elements must be equal, which means that there's no two distinct elements in the domain that are mapped to a single element in the target. For example, in this figure, as you see, A and D are both mapped, B and D are both mapped to W, right? B is mapped to W and D is mapped to W. Therefore, this function doesn't represent a injective function because, as I said, if you have two distinct elements in the domain, they should be mapped into different elements in the codomain, but here B and D are mapped into the same element in the target, which is W. The next definition is surjectiveness. A function like f is surjective or onto if and only if range of f is equal to the target of f, which is y. So we have seen the definition of range. So what does it mean when we say range of f is the same as target? It means that for every element in the target, like y, there should be an element in the domain such that x is mapped to y. That element of domain, which is x, is mapped to y. Again, for every element in the target like y, there should be an element in the domain like x such that f of x is equal to y. For example, this is an onto function because the domain, because the target, which is t, which contains 4 elements, is equal to the range because the range is also w, x, y, and z. In other words, all the elements in the target are participating in the function, which means every element in the target, for every element in the target, there's an arrow towards it. This is a function that is not onto or not surjective. Why? Because, for example, z is in the target, but it's not in the range. Why? Because there's no element in the domain that is mapped to z, because no arrows goes toward element z. So we have provided the definitions of injective and surjective. Finally, we define bijective. A function is called a bijective function or a bijection, or a function is called a one-to-one correspondence if and only if it is both injective and surjective. So a function that is both injective and surjective is called a bijective function or a bijection or a one-to-one correspondence. So as I said, the first function in this diagram is onto, but it's not one-to-one. The second function is not onto, but it is one-to-one. Why is it one-to-one? Because you don't see any two distinct elements in the domain that are mapped to a single element in the target. Every element in the domain is mapped to a different element in the target. So this is a one-to-one function. And finally, the third diagram shows a bijection. Why? Because it is both one-to-one and onto. Why is it one-to-one? Because for every two distinct elements in the domain, they are mapped into different elements in the target. That's the definition of being one-to-one. And it is onto because all the elements in the target are also the elements of the range of the function f. So remember, when you have an onto function, the size of domain should be greater than or equal to the size of target. And when you have a onto function, when you have a one-to-one function or an injective function, the size of target should be greater than or equal to the size of domain. And when you have both properties, because the domain should be smaller or equal, or larger or equal, and larger or equal, we have no choice but to say the domain is equal to the target in a bijection or in a bijective function. Finally, we talk about Boolean functions, which are a specific type of functions, and they are very useful in computer science. So we start with some preliminary definitions. First, we talk about Boolean algebra. What is Boolean algebra? Boolean algebra is a branch of algebra that contains a set of rules and operations for working with variables whose values are either 0 or 1. So Boolean algebra is a set of rules and operations that are working on Boolean variables. Boolean multiplication is the first operation that we define in Boolean algebra, which is denoted by a simple dot, and it applies to two operands, two elements. Each one of them should be either 1 or 0, and it obeys the standard rules for multiplication that we know in that we know in algebra. Basically, 0 times 0 is 0, 0 times 1 is 0, 1 times 0 is 0, and 1 times 1 is 1. These are all the possible cases that a Boolean multiplication can have. And you can map Boolean multiplication to a logical conjunction. How? If you assume that 0 is corresponding to false, and dot or Boolean multiplication corresponds to conjunction, and 1 corresponds to true, then you can have the same equation or the same operation in logical conjunction. For example, conjunction of f and f is f, the same way that multiplication of 0 and 0 is 0. Conjunction of false and true is false. This is the translation of 0.1 is equal to 0. Conjunction of true and false is false. That's a translation of 1.0 is equal to 0. And finally, the conjunction of true and true is true. That's a translation of 1.1 is equal to 1. Next, we define Boolean addition, which is denoted by a plus sign. Boolean addition is a little bit different from standard addition in algebra, and I'm going to talk about the difference. So first of all, Boolean addition again has two operands, two elements. Each one of them should be either 0 or 1. And it obeys the standard rules of addition, except the fact that 1 plus 1 in Boolean addition is equal to 1, not 2, because 2 is not defined in Boolean algebra. Everything should be either 0 or 1. So 1 plus 1 is defined as 1. So here is the Boolean algebra. Here is the Boolean Boolean addition. 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1. However, 1 plus 1 is not 2, it's equal to 1, 2. And you can map a Boolean addition to a logical disjunction if you apply the same correspondence that I said before. 0 is corresponding to a false, 1 is corresponding to true. So false or false is false, false or true is true, true or false is true, and true or true is true. So that's a correspondence between Boolean addition and logical disjunction. So next we have another Boolean operation which we call it complement. Boolean complement is corresponding to logical negation. So the complement of an element, which is denoted by a bar symbol, reverses that element's value. So if the element is 1, it becomes 0. If it is 0, it becomes 1. So the Boolean complement of 0 is 1, Boolean complement of 1 is equal to 0. This in the same way that negation of false is true and negation of true is false. Next, I'm going to define some terminologies. Variables that can have a value of 1 or 0 are called Boolean variables. And Boolean expressions can be built up by applying Boolean operations that we have seen so far, like complement, addition, and multiplication, by applying those operations to Boolean variables or to the constants 1 or 0. So if you apply different Boolean operations on Boolean variables or the constants 1 or 0 in a nested way, for example, you apply one Boolean operation on a set of variables and then apply the result on another variable using another Boolean operation. This way you can build a Boolean expression. In the next slides, I'm going to show you some examples. So here is a Boolean expression like x times y plus 1 times z bar. So here we have a multiplication operation between x and y. Here we have an addition, and here we have another multiplication, Boolean multiplication, and z complement is the complement of z. So the complement operation is applied to z and the result is multiplied by 1. So let's see how we can evaluate this Boolean expression when x, y, and z are all equal to 1. So obviously the multiplication has a higher priority than addition, so you have to first multiply x and y and then add it with the result of this multiplication. So 1 times 1, which is x times y, is equal to 1. So you replace x times y by 1. And then you write the rest of the expression, which is plus 1 times z bar. Also, it's important to note that complement has a higher priority than multiplication, so you have to first apply the complement on z. Since the value of z is 1, the complement of 1 is equal to 0, so you can say in the expression you can replace z bar with 0. So 1 times z bar becomes 1 times 0, and 1 times 0 is equal to 0. So the first part, x times y, became 1, the second part, which was 1 times z bar, became 0. So 1 plus 0 is equal to 1. That's the final value of this logical or this Boolean expression. Let's see another evaluation of a Boolean expression. Here we have x plus z times 0 plus y bar. The complement is over this addition, so we have to first do the addition. In this case, we assume that x is 0, y and z are 1. So since y is 1, 0 plus 1 is 1, and 1 bar is equal to 0. So we can replace that parentheses with 0, so we have x plus z dot z times 0. Z times 0 is equal to 0 because no matter what the value of z is, any number times 0 is 0. And finally, x plus 0 is equal to, x is set to 0, so 0 plus 0, and 0 plus 0 is equal to 0. Here are some laws for Boolean algebra that you need to remember. You don't need to remember the names. Basically, these laws are very familiar for you because we have seen them in the last in the last two chapters that we have covered. Basically, the first law is called idempotent. You remember this law for logical equivalence of P or P or P and P. Here, instead of disjunction, we have addition. Instead of conjunction, we have multiplication. So these are the translation of those laws that we have seen for logical equivalence, but here we replace addition, we replace disjunction with addition, conjunction with Boolean multiplication, and negation with complement. So I'm not gonna go over them because we have seen them a lot before in the last two chapters. So try to take a look at them and see how these laws are translated in Boolean algebra. The only law that worth noting is De Morgan's law, which says x plus y bar is equal to x bar times y bar. So negation or complement in Boolean algebra, if is applied on an addition, it converts the addition to multiplication. If the Boolean complement is applied on multiplication, it converts multiplication to a Boolean addition. So you can see the rest of laws and think about their correctness. Here is how we can simplify a Boolean expression using the laws that I showed you in the previous slide. Let's assume that you want to simplify x times y plus x bar y plus z times y. We first can use distributive law and factor out y from the first two terms. If you factor out y, you have x plus x bar times y plus z times y. And then if you use a complement law, you can replace x plus x bar with 1. So it would be 1 times y plus z times y. Then you apply identity law and say 1 times any variable is the same as that variable. So 1 times y is the same as y. So you replace 1 times y with y. And then we apply distributive law again and say you can factor out a y, and the result would be 1 plus z times y. And 1 plus z is equal to 1 because of the domination law. And 1 times y is equal to y because of identity law. So we saw that this whole expression is the same as only the variable y. Finally, we talk about the definition of a Boolean function and the way to represent it using a table. A function like f with domain 0 and 1 to power n and targets 0 and 1 is a Boolean function with n input parameters. So as you see, the target can be only 0 or 1. The the target is a set containing only 0 and 1, and the domain is the set 0 and 1 to power n. What does it mean? It means that we apply the Cartesian product on the set 0 and 1 and itself n minus 1 different times. For example, 0 and 1 to power 2, 0 and 1 squared, is a Cartesian product of 0 and 1 and 0 and 1. So if you multiply 0 and 1 by itself only once, it becomes 0 and 1 squared. What is 0 and 1 cube? It is when you apply Cartesian product on 0 and 1 and itself twice. Then it becomes 0 and 1 cube. A Boolean function with n input parameters has a domain equal to 0 and 1 to power n. So for example, if we have a function with 3 input parameters like x, y, and z, you can represent that function using this representation, f of x, y, and z. Here we have an example of a Boolean function. You can represent a Boolean function using a general formula like this. The general formula should be a Boolean expression which contains those variables that we have specified as input parameters of that Boolean function. So this is an example. F of x, y, and z is equal to y times z plus x times y bar. Previously, I have shown you how to evaluate a Boolean expression when the variables are set to constants like 0 or 1. So using those evaluations, you can construct a table that we call it input-output table like this, that shows the output value of the function for every possible combination of input values. Since we have 3 input variables x, y, and z, there are 8 possible combinations of input values. The first combination is 0, 0, 0, 0, 0, 1 is the second one, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. It is similar to truth table, but instead of true we have 1, instead of false we have zeros. And then in the last column you can write down the value of the f of x, y, and z by applying by replacing x by 0, y by 0, and z by 0 in this Boolean expression, and find the value of this expression by evaluating it. So you can evaluate this function with this general formula 8 different times for each of these possible combinations of x, y, and z. And then you can fill out this table.